So I guess we're ready to start. It is my pleasure to introduce Jose Luis Tain. He comes from Spain, from the University of Valencia, where he has worked in several astrophysics-related experiments. He has done some work at Intel, measuring neutron capture rate, important for the gas process. He has done also some nuclear structure stuff using task measurements. And lately, he has been doing the delayed neutron emission probability measurements at BRIKEN, and that's where he's here today.
Okay, thank you, Fernando, for the introductions, to JINA for invitation to come here, and Fernando proposing me. I have to say that I missed the purpose of the talk, so I thought that audience was different. I see many students and so on, so I didn't prepare the right talk for this. So I will try to downgrade my presentation just to allow most of the people to understand it. I just learned it this morning. So what I want to present is this BRIKEN project, which is it's a project that we started a few years ago, and that has been taking data for the last 2 years at BRIKEN. And the idea is to make extensive measurements of beta delay neutron emitters, nuclei that after beta decay emit neutrons, with an emphasis in using this information for astrophysics, but also for nuclear structure, and also for the purpose of studying the process of delayed neutron emission itself. So I will briefly give some ideas about what is the emission, beta delayed neutron emission process, what is the relation with astrophysics, more specifically to the R process. I will describe the instrument that we are using for that and show a few examples of results, very few because we are still analyzing the data. The last experiment was done in November. So beta delayed neutron emission was discovered by Roberts very soon after the fission process itself was discovered. Delayed in this context means retarded with respect to the fission, in opposition to the neutrons which are emitted from the highly excited fission products, which are the prompt neutrons. And very soon afterwards, in this very important paper by Bohr and Wheeler, where they explain the fission process, they give the correct explanation for the process. And what happens is that when you go for very neutron-rich nuclei, the neutron separation energy, that is the energy that you need to expel the last neutron, so to say, from a nucleus, lowers, and it can become smaller than the window that you have available for the beta decay, the so-called Q beta value, so that you can decay to states which are above this neutron separation energy, which are unbound states in the nomenclature of the reactions. That is what we call a resonance. And from there, you can emit either a gamma cascade or a neutron. And because of the nature of the interactions, that the strongest interaction is much stronger than the electromagnetic interaction, the preference is that you emit neutrons instead of gamma rays. So you have beta decay followed by neutron emission. Typically, the people assume that there is no competition possible of gamma emission respect to the neutron emission, but this is not true. And actually, we have been looking into that using a different technique, a total absorption gamma ray spectroscopy. And we have seen that for a number of cases, the gamma emission can be comparable to the neutron emission, let's say the integral value. And this comes because you can have neutron which is kinematically hindered. I mean, because when you look into the levels, nuclear structure levels that are available for the decay, you can only do the jump with a very large L value, orbital angular momentum, and this is kinematically forbidden. So then the gamma emission can compete and can be eventually very large compared to that. So it can happen also that the two neutron separation energy is lower than the Q beta window, and then you can have the possibility of having two neutron emission. And typically, you imagine that as a process that you have first one beta decay, and then a neutron emission, which populates the states here, and this again either emits a cascade, gamma cascade, and then emits. So it's a sequential process, what you typically think of that, okay? The important parameters for neutron emission is the probability that the process occurs, and we distinguish normally between the probability of 1 neutron, 2 neutron, 3 neutron emission. The sum of all of these will be the total neutron emission probability. And another very important parameter is the neutron multiplicity, how many neutrons you need per decay. And this is just calculated like that. Okay, so this is a formula. So you can calculate that, the neutron emission, and actually it's very much related with the beta intensity, the distribution of intensity to all the levels in the final nucleus, which will be represented by something like that. And this is this quantity here. And actually, instead of that, often the people write it in this another quantity, which is the beta strength, which is related with the beta intensity by this Fermi phase space rate function, which simply remove from the intensity the part which is due to the phase space, the energy available for the decay. There is a very strong dependence on that. So it is very different, the beta strength distribution from the E-beta distribution. I mean, the energy dependence of this function is something like energy to the 5th power, close to the endpoint. So this beta strength is what you have here, and you can see that you can calculate it by an integral of the intensity weighted by this factor here, which is the ratio between the total emission probability, the channel-specific probability to the total emission probability. You can see also that the half-life of the decay is related with this quantity. And actually, you can see that both are intimately related because of this beta strength. Okay? So this is something very important to remember. And actually, the beta strength can also be calculated in this way. And this is an element of a matrix element, reduced matrix element between the initial and the final state mediated by the beta decay operator. So actually, when the theoreticians calculate the half-life or the Pn value, what they calculate is that, and then they use this formula to obtain the half-life and the Pn value. Okay? So one caution that one has to treat is that the treatment of this ratio between the specific channel and the total is done very schematically, or has been done very schematically until now. Typically, you ignore the gamma competition. You say that if it is possible, it always indicates by neutron emission. Moreover, and this is more difficult to understand, typically they assume that if 2 neutron emission is possible, then it overtakes to 1 neutron emission, okay? And so on. So it's kind of, they call it, I forgot the name, sharp cutoff model for that. The other thing is that when you make this calculation, theoretical calculation, typically you get very few levels, and then since the probability is just an integral, you can have that the level is just close to the border, to the neutron separation energy, just by chance, because the calculation is not very precise. And then you can have some kind of very strong oscillations between the number because of that. And the people what do is introduce a schematic spreading, because the calculation in itself is not able to provide the spreading of mixing with many levels that normally exist around the levels that you are calculating. If you look now, ask you the question, how much we know about the beta delayed neutron emitters, you can look into this picture. These black dots are experimentally known values. You have here numbers of P1N, P2N, P3N, and P4N that has been measured. And you have here, for comparison, the number of known emitters, which will be possible 1N, 2N, and so on emitters. And you can see that there is a very large discrepancy, okay? By the way, these numbers are coming from the latest evaluations that have been done. These are one already published, one is already submitted, that has been done with a so-called coordinated research program of the IAEA that has been trying to, let's say, put, because the last evaluation was from long ago, and to put the field in a more up-to-date level. What you have in the background of the figure is one of the calculations of these beta strength calculations transformed in Pn value. This is a popular one, and it's done within the so-called QRPA approximation or model. And it's based in an energy scale on ground state properties calculated by a so-called finite range droplet model This is by Muller and collaboration and was published in 2003, and it has been used many times to make this type of calculations. And you can see here that as you move away, the neutron emission probability overtakes, and you have some 100% of neutron emission probabilities. And this gives you a hint why this is important for astrophysics for the R process. In the R process, what you are having is a burst of neutrons which creates, through a succession of rapid neutron captures, a very neutron-rich nuclei that eventually are stopped. In the classical hot air process idea, you stop it because you have the opposite reaction, which is gamma N reaction, active, and then it is no longer possible to produce more neutron rich, and this beta decay, and the process happens iteratively so that you can climb this kind of ladder up to the very high numbers. The number of nuclei that you are producing here in this, you establish kind of a continuous flow, is related or is proportional to the half-life of the nucleus, of the beta decay of this so-called winding point nuclei. When the neutron that you have for the process are exhausted, then you have decay back to stability. If there were no neutron emission process, it will be a diagonal here, this way. But if there is a neutron emission, then you will move one mass unit or two or three mass units depending. So it's at the end, you arrive to the stability, to your abundances that you observe in a different way. And this has an impact. So obviously it has an impact to the final abundance. There is also another effect, is that these neutrons that you are injecting in the system, after the initial ones are exhausted, they can be again captured in an activation of the process, so you can have an opposite effect. So you will move the mass distribution to higher value. So at the end, the effect is a combined effect of the two. By the way, here, the background is another calculation. This one is a very similar model. It's also a QRPA model, different way of calculating the ground state properties and an energy scale from marketing, which was published more recently. And you can see here, again, that the number of neutrons emitted close to the limit of the stability is very high. Yeah? And another way to looking to the importance of this neutron emission probability is to look to sensitivities of the abundance that you calculate related to the specific nuclei. This is a way to have an idea. This has been done in this paper by Moonpower et al., both for the half-life and for the PM value, and for different trajectories, which are closer to the stability and farther from the stability. These are so-called hot trajectories. This is a cold trajectory, and this is a trajectory which will correspond to a neutron star merger. And you can see that, in fact, the influence of neutron emission goes to more exotic as when you move to these other trajectories. So this is somehow the reason why it is important to measure these nuclei, because at the moment, all these nuclei are very far from the experimental reach, and we have to rely on theoretical estimates, okay? And this is the idea behind the BRIKEN project. We want to improve our knowledge of these quantities in order to, if not measuring directly the nuclei that we are going to produce, at least to improve the theoretical calculations. And you can ask you, first, the question is, I mean, how good are these calculations that we have available now? Or how reliable it is? Reliable means you compare with experiment and see, I mean, how different they are. And you can see here for this first calculation that I mentioned you, how it compares to the experiment. This is the PM value, total PM value compared to what is known for the nuclei at that time. Practically now, nothing changed. And you can see that the agreement is within, let's say, a factor of plus minus 10, factor of 10, okay? This is the kind of agreement that you get with there is an improvement when you go in this direction, which means highest PM value, which means farther away from the stability. And this is because the importance of the beta strength gets smaller, because the energy factor is more important. Yeah. So this part of the improvement is because of that. You can also ask yourself how different are these calculations, and these are some plots. For example, this compares these two calculations that I showed you before, and you can see, for example, that here there are huge discrepancies, and this is in part because there was some problem with neutron emission probability calculators in this model calculation for the very most exotic nuclei. And you can see here another comparison. This is another totally different model. This is so-called gross theory model, and with another mass model by Cora and collaborator. And you can see again that there are regions where the discrepancies are very large, although it looks like at some point they more or less agree. Very recently, actually, last week or the last month, there was a publication by Meller and collaborators where they somehow improved the original calculations by the inclusion of competition. This is what I mentioned at the beginning that was not including competition between the different decay models. And this is done within a framework of a model which is called the Hauser-Feshbach theory. And actually the idea is there that you calculate the gamma width and the neutron width by means of statistical average quantities, which are the level densities, so-called photon strength function, and the neutron transmission that you can calculate with an optical model, and you can combine them to obtain these numbers. And this, including that and the sequential process, then they are able to introduce for the first time in global calculations this competition. And you can see that there is, in fact, large differences appear because of that. And we will see later more on that. And here you have a similar picture related to the half-lives. Again, here comparison with experiment. Again, you have very large spreads. This again a factor of 10 lines that you have here. Then again comparisons between different theories or models. Let's say like here, you see there are regions again where the discrepancies are very large. So again, this means that better you have experiments in order to further improve the situation. And if you ask yourself, what is the impact of calculated half-life or different calculated half-life or different calculated PM values into the abundance that you calculate, this is what you have here is the so-called solar abundances in the region of 120 to mass 120 to 200, where you can see the second and the third are process peaks, and here in between the rare earth peak. And in this plot here, you see the comparison. This is from the paper from marketing, a comparison between the Meller calculation and his calculation. And you can see that there are significant difference in the prediction by using the two different half-lives for a hot air process and also for a cold air process, which is far away from the stability. You can also see that there are significant differences between the two. And if you look into the PM value, now this is graphics is coming from a paper by Almudena Arcones. And again, you have the solar abundances compared with the calculation. In this case, we have as a reference calculation in black, the Muller calculation, and in green, it's just a calculation where you remove completely the possibility that neutrons are emitted. And you can see that in the hot air process, apparently there is no impact here, while in the cold air process, you see a bigger influence. But something that is very important is that if you plug the neutrons in this calculation, but you do not allow that there are captures after the first burst of neutrons has exhausted, there are no secondary capture reactions, you see a huge effect. So actually, there is a compensation between the neutron emission effect and the capture effect. And I can tell you that the capture cross-sections for these nuclei are even more uncertain than the PM values or the half-lives. So there is something there that has to be. The reference line is the same here, it's Muller. It's below, here you can nearly not distinguish, you can see it there. Yeah, in the both, yeah, right. So ultimately, in the context of the R process, studies, what you want to understand are the physical conditions where how the process itself is occurring, what are the different sites, either you talk about core collapse supernova, where you can produce this high neutron flux, or a neutron star measure, something that very recently has become very popular because we have observed for the first time the fusion of two neutron stars through gravitational waves and also through electromagnetic spectra. And there is a strong hint from the evolution of the color of the light emitted that in fact we are observing on the moment the production, the fabrication of these very heavy elements in the process of the neutron star merging. For that, what we want to do is to reduce as much as possible the uncertainties of the nuclear physics input parameters that go into calculation. And in this respect, I think it's very important that we keep the original idea that instead of testing a model against the half-life, which is what has been done until now, you test it both to the half-life and the PM value because the two quantities are not independent, as I showed you at the beginning. I think this will improve very much the calculations. So that is the idea behind the BRIKEN project. So we decided, actually after an experiment that we did at GSI many years ago, we got an experiment approved to measure in the lead region. And then we find out that Fernando had another experiment approved in the Tain region. So then we combine efforts. So instead of moving the neutron detector, which is here at MSU, we use our neutron detector for making the two experiments, which I think were rather successful for what we did. So we were enthusiastic, and then we say, why not to move to another place where we can make this measurement just now? And the place is BRIKEN, because at BRIKEN you have this RIF facility, which produces very high intensities beams at the moment, which are producing very high intensities. They have these big RIPS spectrometer, which is a very nice spectrometer, able to separate the products of the reaction, and so we can fabricate these very exotic nuclei and then bring them to our setup and make the measurements. And in order to cope with that, we use two detectors, IDA, which serves to detect the ions which are implanted and their subsequent beta decay. And then we develop a new helium-3 moderated neutron counter. The project involves something like 20 institutions and about 50 participants. At the moment, we have had 6 proposals approved, which more or less, as you see here, try to cover the whole range. From the 6 proposals, we managed to complete 3 proposals until now, which is the one around the nickel 58, the one around mass 100, and the mass around mass 130. And we were able to nearly complete this one here, 75% of the meantime, which is around the rare earth elements. The red numbers indicate what we expect to achieve. And you see, if you add all of them, this is impressive because we are saying that we are going to measure 235 P1N values, 90 P2N values, 70 P3N values, and 5 P4N values. And we will get something like 115 P1 half-life, if what we promise is true, okay? So we are in the process of proving that this is correct. Sorry? For the light one, yes, yes. So all the experiments will use, this experiment will use a uranium beam, and this one here will view with a light beam, which, not calcium probably, but maybe zinc. Yeah. There is, yeah. What was your question?
No, actually, okay. The one that was really for light, like
yeah, yeah, yes, as to mass 40. Yeah, but calcium is probably not available there. Yeah. Okay, so it's exhausted the calcium 48. So I don't think there would be possibility to make a measurement. So we are thinking. Yeah. Yeah. No, as far as well, maybe we talk later. Maybe I do not understand it. Okay. So I just go through the detectors. So the first detector is where we implant the ions that have been produced and separated by the Mach separator, by the fragment separator. This is AIDA. This is a detector coming from the UK, and you have there the institutions. The current setup that we are using is a stack of 6 double-sided silicon strip detectors. They are pretty large. They are 7 centimeters by 7 centimeters. The strips are half a millimeter width, which is exceptional. Normally they are thicker width strips. And that has advantage and disadvantage. The main advantage is that we have to deal with 1,540 channels, which is a lot, and makes life very complicated in the analysis process. It has its own integrated electronic and DAC, and you can see here that it can achieve a rather good spatial resolution between implant beta, and this is important because we are going to implant something, an ion that we will, with information from the big ribs, identify as a specific ion, but then later the beta decay will happen whenever, and we don't know how to correlate that except statistically. So what we are going to do is time correlate the implantation and the decay, and for that, in order to reduce the background, you have to correlate them spatially. They have to be coming from the same pixel. Otherwise, you have too much noise. So this is the idea behind. So in this respect, this is the segmentation is good. The other question is that this has 2 different electronic branches, one to detect the implant and the other for the betas, because there is a huge difference in the energy that you are depositing in the detector. The implants are hundreds of MeV, the betas is less than 10 MeV or whatever. So in order to allow a fast recovery after the implantation, we have 2 branches, so we are able to look into the beta branch with timings which are very short. That is the idea behind this detector. Now, the neutron detector. The idea for the neutron detector is a classical idea, is that you have neutrons are emitted with energies up to a few MeV, and then in order to efficiently detect them, what we do is we slow down them by allowing them to hit hydrogen nuclei, I mean protons, and when the energy is low enough, if they find a tube which is filled, a proportional tube which is filled with helium-3, then these reactions happen very easily with a high cross-section, and you produce a proton and a triton, and you liberate 0.7 MeV, which are easily detected, okay? And actually, if you look for the spectra of that, it looks like that. You see that it's not exactly a peak, and there is a tail here, and this has to do with what we call a wall effect, is that if the capture happens close to the wall, it can happen that one of the 2 ions is not able to deposit the full energy. So this produces this tail. But still, you can see that compared to the noise, it's very well separated, and this makes these detectors very specific to detect neutrons, and they are very, very, very good. There is one advantage of this idea, is that the detection time can be very long because it needs time to moderate. And you can see here the moderation time, it can be of the order of 200 microseconds, so to say. And this is a long time if you think in terms of data acquisition. If you were going to make a conventional event-based data acquisition, you will introduce a gate of 200 microseconds, and then this will introduce a lot of the time if you want to measure that. So this is not the idea. So the arrangement that we are using now is similar to that. We have something like 100 helium-3 tubes. The tubes are coming from BRIKEN, from Barcelona, and from Rock Ridge. I mean, the colors indicate the procedure, the procedence. We make an arrangement of these tubes in order to get the maximum efficiency possible and the flattest efficient possible in a rather large energy region of to 5 MeV. You can think that this is not very flat, but I can tell you that this is very challenging to obtain something like that. Actually, this was a dedicated work by Ariel Tenifeño in Barcelona in order to produce such a very flat efficiency curve. The idea is that we can have, since we are very far from stability, we can really have decays that produce, and we know already because this had been measured by bundle, that we have some decays that have 5 MeV neutrons, which is something exceptional in the field until now. Okay, so this is a Monte Carlo calculation, for calculation that we have now cross-checked by looking to Californian source measurements and by looking to some nuclei which have well-known PM values. So this 767%, I didn't put the error bar, now I see, is just the efficiency for, let's say, the less than 1 MeV, or let's say a conventional beta N emitter, okay? And it drops by 25% up to 5 MeV. So this means that if we have a very unlucky situation, we can have a, let's say, a decrease of efficiency by 10%, something like that.
It's enough for getting free, or you planning to increase?
Oh, if you look into this, we have other configurations. This is what I wanted to tell. We have other configurations. We only have tubes, up to 166 tubes, and we can get efficiency of the order of 78%. Okay. The question is that we decided to include also gamma ray detectors. So we have included 2 gamma ray detectors for the purpose of making nuclear structure studies. So they are inserted on the sides, and this makes the life more complicated. And this is the reason that we don't get such a high and not such a flat efficiency. But we still decided that this was the best option for us. And as I mentioned before, the conventional data acquisition system is not good for that. So we use the acquisition system that was developed at Valencia, which is a so-called self-triggered, triggerless system, where every channel, every tube, it fires the ADC, and the information is recorded independent from the other tubes. And this is very useful because it reduces the dead time to a negligible amount. And it is based in digitizers fabricated by a German company, which is called Struck. And we also use that for the Clover and other ancillary detectors. And one particular thing that we have to solve is that we, in order to check that everything was working, we try to make an analysis online. And this is very complicated. We have 3 independent data acquisition systems, one for the neutron detector, one for the big crystal experimenter, and one for AIDA, and we have to combine that. So we make an effort to make a program that from the source, from these original trees, we'll make a merged program. And so in about 1 hour after we finish a run, we can look into the data and see the experiment. So we are sure that we are not making a stupid mistake in the experiment. So this is a total arrangement. You can see here the detector itself. You can see the tubes protruding there, the Clover detectors. AIDA is coming from behind. You have here a sketch of how this is organized. And this here is a shielding that we put to try to stop neutrons which are coming somewhere here from the beam. And I have also to mention that in some runs, we replace the AIDA detector by another detector, which is also a silicon strip detector, which is called Wasabi, which is from BRIKEN. And in combination with a detector which was developed at the University of Tennessee, which is a WISO scintillator red with a flat panel. So it's many crystals, small crystals. So it's not a silicon detector, it's a scintillator detector. And it has some advantages. And this was used in the So the most important issue that we found in the experiment is that the neutron background induced by the beam is huge. Okay, it's up to 200 neutrons per second. For reference, the natural background is 0.4 neutrons per second. And this is a very nasty thing. And we tried many things to reduce that. The beam intensities during our runs, oh, you mean the secondary beam intensities? Yeah, up to 500. No, 1,000. Yeah. I mean, this is produced by the beam, high energy beam. It's a very high energy beam, 300 whatever, in some point of the spectrometer, or in the materials that we have there in the detectors which are along the spectrometer, and also probably in AIDA itself when it is implanted. And we try to make everything to reduce that. So we remove as much material possible close to the detector. We found something very important, is that a way of doing that is that you see here, there is the last classic detector in the beamline of the big crystal spectrometer allows us to know when the ion is coming here. So we bet on any neutron which is produced within 200 microseconds after this ion. And this is very useful because it reduces a lot the neutron background. For example, the 1 neutron background by factor 2 or 3, the 2 neutron background by a factor of 30. Okay, so it's a huge improvement. Yeah, even though it's not enough, and we had to use beta tagging, so we cannot make ion-neutron correlations for our study. We have to use beta tagging as a mean to reduce the background. And even though we have still to, in the analysis, correct for the correlated background that happens, that you have a beta particle which has no associated neutron, but it picks up a neutron, random neutron, and it simulates a P1N value or a P2N value. It can be that you have a beta particle that has 1 neutron, and then it picks up a random neutron, and then it mimics. And you can see here, and this is very important when the PM values are small. You can see here, for example, this is a small PM value for 80 thing. This light blue thing here is random coincidence. We have developed a method that allows us to calculate that precisely and correct. Or you can see here, 83 gallium. If you look to a raw spectra, you think that 83 gallium is a 2 neutron emitter. No, when you make the correction, there is nothing there. Okay, so this is an important thing.
I understand the main neutron background coming from the reaction as a degrader in front of AIDA.
Not necessarily. This is what our idea. Actually, we don't know exactly all the things. I mean, one problem at BRIKEN is that you cannot make a commissioning run. So we have to learn things while we are making the experiment. So we cannot do anything while we want to check that. We are convinced that a lot of the neutrons are coming from the spectrometer generated at some point. There is something very, very funny is that you change the setting of the big fixed spectrometer, and then you change the proportion of background.
I was thinking if the degrade is.
Yeah, we change for it. Yeah, for example, we do that. We remove as much as possible degrader there. And we also try to check that if, for example, we use aluminum normally, and we used to put, for example, tantalum, and the effect is very small. Okay, yeah. Now I show you very briefly, I mean, some results. Not many, because we are still, as you see, fighting with the analysis and trying to learn things. The sorting of AIDA is something very complicated, and we are still trying to learn what is the best way of doing that. But I just scanned the few proposals which have been run. This is the first experiment that was run. It was a region of 78 nickel. This is so-called identification plot that you see here, where you see the set and the A over Q, the typical way that you organize that. This information is coming from big ribs, and then you can see clearly what are the nuclei. So then you select that nuclei, and then you can make your time correlations, and then you can analyze that. And you can see here the identification plot, the range of nuclei that we were able to measure. And here, for example, you see that the line that corresponds to the previously measured PM values and the line of the previously measured half-life. So there is a number of new information which is coming already here. And for fun, here is represented the nuclei that we are seeing in comparison with the calculations for half-lives and PM value, so that you have the feeling of how much different they are. And the first thing I wanted to show you is, well, I didn't mention it, but we were able to measure 78 nickel In this experiment, we implanted more than 7,000 ions, which is, I mean, an achievement in principle in itself. And from that, we can observe the neutrons very clearly, make the analysis of the P1N value for this nucleus, and we obtain a value which is 25%. Okay, and then you can do the exercise of. We also obtained the values for all lighter nickel isotopes, 77, 76, 75, and then you can compare that with a theory, with what you have available in the market, so to say, and then you can see that our numbers where no theory goes. So all these calculations, the QRPA calculations, the several QRPA calculations seems to be higher than the data, and this growth theory calculations is smaller. Okay. We also compare that with previous knowledge for these nickel isotopes, which come from MSU, an experiment made by Hosmer et al., Henrik, and so on, years ago. In 2010, it was published. And you can see that our numbers are smaller than these numbers. Okay, this one has a very large error bar, anyhow. And there is also an experimental, not unpublished value for the P1N value of 78 nickel, which comes from the thesis of Xu, but this number is obtained from gamma ray spectroscopy, only looking to the gamma rays and making some assumptions on how the intensities go. So it has some ambiguities, and this number is the one that you see here, okay? And well, as you can see here, for this shell closure, for this double magic nickel 78, there is a huge spread of theoretical estimates. Sorry, I forgot to mention, this is a shell model calculation, and this is the highest of all of them, okay? Okay, so somehow this gives you a feeling of what you can find. Another important thing, this is from Rin Yokohama from the University of Tennessee. He has provided this slide. And this is something very interesting. It's related with what I told you before about the competition of different channels. I mean, the fact that you don't introduce competitions and that you say that if 2 neutron emission is possible, then there is no 1 neutron emission, is that you exaggerate the 2 neutron emission with respect to the 1 neutron emission, okay? So what this first experiment shows for the gallium isotopes is that it's just the wrong. But at some point, I mean, this was logical because it cannot be like that. So you see here the gallium isotope, the P1N values for the gallium isotopes, and the P2N values here down. And in comparison with the 2 Meller calculations that I showed you before, the one that did not include the competition and the one very recent that included the competition, and then you can see that by that, this goes up, and then there is a fairly good agreement with our experimental numbers, and this one goes down, and again, there is a fair agreement with experimental numbers. So this means that this is actually essential thing to introduce in this calculation. And this will have an impact in the calculation of the abundances. Here is an example. You will be populating, creating 95 gallium, so to say, in the air process. Then how it will decay back to the stability will depend on this. And you see here that the differences are clear. Yeah, when you include the Hauser-Feshbach model to complement, you see that it goes more straight than if you don't include that. Okay. For the second experiment, the one from Alfredo, Giuseppe Lorusso, and Fernando Montes, this is an identification plot. And then I'm going to show you that Fernando showed you already last week. These are some preliminary results for a change of isotopes from silver to tellurium. This is the experimental. And this, what you have here, is calculated the same isotopes that you have here, and they are not superposed, but if you look carefully and these lines indicate you can see there are, for some isotopic chains, there are very marked differences. So compare that with that, or compare that with that. Okay, so there is a strong difference with the calculation. So it's not, so the beta strength calculation is not correct. This is what it's telling you. I mean, and even, I mean, Fernando and colleagues that have put this new preliminary data into calculation of abundances, and you can see here that, in fact, they found that there is a impact in the calculation. The green will be without the new data, and the red without data, and you can see that between the second peak and the red peak, there is a significant impact of these things. And then if in the mass 100, I cannot show you anything else than this identification plot. This is what we expected to obtain, and then you can compare what we have achieved or not. It's a complicated plot. You can look at that. I don't know what to pray. And for the last proposal that we measured, this rare earth proposal, we have made already 2 runs separated in the time. The first one was for the heavier nuclei. The second one for the nuclei lighter. You can see here, this identification plot doesn't look so nice. And this is because there is so-called charge states that appear. So the ions that come, they are not fully stripped. They get 1 electron in the way, and then the identification becomes not clear. I mean, they are changing position, and that can be eventually problematic. And actually, in this second round, the people from Big Trips, from the spectrometer, make a very nice work, and we have a much clearer situation for this second implantation. And you can see here an example just from the online plots. Yeah, the PM1 value for a rather exotic nucleus, which is 157 praseodymium.
You can stop these, you can separate the quantum energy and the detectors.
Again?
You can stop beams, you implant,
yes.
Can separate the charge states and the
yes, we can make some things to separate that, yeah. I mean, actually, we have some additional detectors in the beam line, which I didn't say. We have some silicon detector, so calculated delta E, and so on. And then we can make some improvement on that. Yeah, okay. Yeah, okay. So, I think it's time, no? Yeah, so the summary. I think I can say that the BRIKEN setup is performing well and that it has been characterized. The biggest issue that we found is that this very large neutron background, which I think is inevitable for any experiment which will be running these very high energy beams. But we have developed means to tackle this problem, and I think we can do that. We have completed 3 proposals. There is a 4th proposal which have been completed to 75%. Until now, we have measured something like 250 nuclei, and we expect from that to obtain 170 new PM values and about 50 new half-lives. Well, the data is still in analysis, as I said, but already we have some important physics results. We see have evidence that it's important to include the competition between the different beta XN channels in the calculation of the PXN probabilities. We observe, again, that there are, in occasions, large deviations between what we measure and what is calculated. We have been able, for the first time, to measure directly the neutron emission for the double magic 78 nickel. And we expect to continue the measurements in fall this year with one of to complete the experiment and maybe to go to the heavier lead experiment, lead region experiment. This is a list of participants. This is taken from a paper. I hope it's rather complete and that they are not missing too many people. Better is to have a picture, but we didn't manage to make a picture of everybody together, so I have here the picture. And if you make the intersection of the two, you will get a better approach of all the people which has participated in the experiment. Okay, and then thank you. That's all.
Since you showed the efficiency that it's kind of flat but not completely flat, and you don't know exactly what neutron energies you have.
Right.
In the experiment.
Right.
So what kind of efficiency and
Yeah, yeah. So this is a part of our systematics. And we are very worried about that. I mean, you can correct for that if you will know the neutron energy distribution, because you can use the Monte Carlo simulation to make that correction. And obviously, we will not know that for most of the nuclei. I mean, in the past, we have done that. We have made corrections of the neutron efficiency using the known energy distribution. Here, this is not a possibility. Then you can do a number of things. You can use the calculation, the beta strength calculation, to calculate your neutron spectra, which is there, and then you can use that as a guess of how much is the correction. Or you can take the most pessimistic approach and say, well, probably there are not going to be worse cases than 84 and 85 gallium, which have been measured by Bandel, and which when you calculate the efficiency, you have the spectrum measured there. It's a reduction of 10%. And then you can say, well, if I don't know anything, I can go, you reduce instead of 67, you reduce by 5%, and you add 5% to your systematics. That is the worst. You will have to decide. There is still another possibility, which is very important, and we have been working on that a lot, is that you can use your detector itself to tell you what is the right efficiency, because the moderation process depends on the neutron energy. The fact that we have several rings, as you remember, we have rings extending time. This means that the neutrons that arrive to each ring have a different distribution, and that the ones to arrive depend on the initial distribution. So there is, in fact, theoretically, is there the possibility that you learn something about the neutron distribution, and then you can correct the efficiency with that. The problem for that is that you need that the Monte Carlo simulation reproduces extremely well. You have to solve an inverse problem. It has to reproduce extremely well the real distribution. And it looks like the Monte Carlo simulation, although it's able to produce the global efficiency rather well, is not able to produce with the correct, let's say with the necessary certainty, the efficiencies per ring. Okay. So we are working with that for the moment. We don't have the solution, but that will be the idea way of doing it.
You mentioned the gamma ray detectors which you have in the setup. And in the beginning, you introduced one of the assumptions that theories usually has a neutron channel is open that one dominates over the gamma ray.
Yeah.
Can you already say something about that from the data? Or is the efficiency which you have for your gamma rays because of the geometry?
The efficiency is very small. We only can see very basically gamma rays of very low range. Okay, the efficiency, I mean, when AIDA is there, the efficiency is 3% of the two Clover detectors. In the runs that we replace AIDA by Wasabi, which is smaller, we could closer the Clover detector, but I think it's 6% or less. So it's very small. We see the gamma rays. We know that we see a lot of new gamma rays, but they are all very low. And the gamma rays that you expect, they will come from above the neutron separation energy. So the ones that have been identified before with gamma ray spectroscopy, where gamma rays go into the ground state, so very large gamma rays. So the things that we have investigated in the past for that is not using high resolution detectors, not using germanium detectors, but using total absorption spectrometers, like the ones that you have here, the sun spectrometer, and the ones that we use in some other places. And this is what have told us that in fact you can see for some nuclei a very strong gamma emission above the neutron separation. I think you did that type of detector for that stuff.
You talked about the experiment and the fault of model 19. Look at this high Z, downstream region.
I think 126.
So you had an experiment to about 19 this year.
Oh, this will be we want. We're planning. We want to propose to to make an experiment with gallium because it's the beam that will be done majority, and then we would like to try the experiment in the left region, which is a very challenging experiment. Actually, you can call it a fission experiment. I don't know if it's what it's called. And to complete the experiment in the third region. Yeah.
You mentioned the very complicated data acquisition. And you said that one of the reasons that you developed it was to minimize the dead time. Do you have a number for the dead time that you have, though?
Yes, we estimate that. Yeah, sure. I mean, when we have to apply that to the real measurement, we have to know what is the effective neutron efficiency, which is not the number that I am putting there. For example, the fact that we use a vector detector for the neutrons diminishes the efficiency. And at that time we calculate, because we have the rate, we have in every channel, we have a pulsar with a precise frequency, so we can compare the neutrons with that, or you can apply, it's also very accurate. You can, this is a so-called non-parameterizable acquisition system, so from the rate you can calculate what is the dead time, and both numbers coincide, and we get in average dead times of the order of 0.5%. Really amazing for the rates that we have. Even much more.
If there are more questions, then the same speaker again.